So let's work through this activity 112 simple machines practice and solve these. The idea being, don't go through here and copy every single one just based upon what I do. But if you get stuck, you have this resource available to you to understand what's going on. So just find the part that applies to you that you're stuck on if you can't get a hold of me, and then use this as a resource, not a copying area. All right, so if we look at the first one here, we have a first class lever in static equilibrium, has 50-pound resistance force, 15-pound effort force. The lever's effort force is located 4 feet from the fulcrum. So we need to draw that. So it's a first class lever, so we know our fulcrum is in the middle. And if you don't know that, then you can go ahead and look that up in the notes. All right. It's in static equilibrium, so it's balanced. It is equally distant from the ground. All right, and I'll draw that a little bit bigger. There's my fulcrum. Here's my ground. All right, and so it's balanced. Okay, and we have a force on one end that's 50 pounds, and I have a force on the other end that's 15 pounds. Okay, this is labeled the resistance force, resistance. This is labeled the effort force, effort. And the last bit of information we have is 4 feet from the fulcrum is the effort force. So this distance is 4 feet. All right, so I've used every piece of information, and if you have struggle putting these together, then go ahead and start crossing things off. I have a first class lever. It's in static equilibrium. I have 50 pounds. I have resistance force. I have 15 pounds effort force. The lever's effort force is 4 feet. Okay, so what is the actual mechanical advantage of the system? So we need to find that equation, and that equation is AMA equals resistance force over effort force. And that's from the lecture notes. Substitute and solve. AMA is equal to 50 pound over 15 pound. Right? FE, FR, FR. And then when I do the math, AMA equals 3.33, right? Pounds cancel. So that is simply the actual mechanical advantage is 3.3. Okay, I probably won't do the math for the rest of them because I don't have a handy calculator or calculator handy. So the next thing it says is using static equilibrium calculations, calculate the length from the fulcrum to the resistance force. Okay, so what are the static equilibrium equations? All right, and in our lessons we learned two things. We said that if it's in static equilibrium, right, in a fulcrum, right, we have moments, which is a rotational force, right? So a moment is equal to force times distance. And the other equation that we said, if it's in equilibrium, the moment around R, the resistance moment, is equal to the moment around effort. All right, so these need to balance out. So we're going to use this equation, right? We're going to use both, really. Okay, and so we have the ME moment on the effort side, the moment on the resistance side. If we know that's force times distance, right? On the effort side, 15 force. Distance is 4 times 4. And then moment around the resistance, 50. because 50 pounds, times, and we don't know this, right, but we have the distance for the resistance. Okay, and so therefore we could put up an equation, since these have to be equal, right? I can write MR, right, so I've laid them out here, 50 lbs, pounds, times dr equals, what's on the other side? 15 lbs, and I made a mistake here. I didn't put my units, lbs, feet, lbs, all right, times 4 feet. All right, and then now we just need to solve for dr. Okay, and I'm going to, if we multiply these together, we get 50 dr, 50 pounds dr. So I'm going to divide by 50 pounds. I'm going to divide by 50 pounds, because you got to do it to both, right? And when we do this, right, the pounds are going to cancel, right? So that's going to leave me feet as my units. All right, and then if we do 15 times 4 divided by 50, right, I'm going to get dr equal to 1.2 feet, right? Because again, feet's what's left over after the pounds cancel. All right, let's look at the next one. So I have a wheelbarrow that's used to lift a 200-pound load. The length of the wheel, so let's do this all together. So if I have a wheelbarrow, right, I have a wheel, right? I've got the stick, and then I've got the bin where the load is. Okay, in the case of this is my fulcrum, right? This wheel is my fulcrum. I am picking up here, right, and my load is sitting here. All right, so I have a wheelbarrow, right? I have a load of 200 pounds. So I'm going to cross that off. The length from the wheel axle to the center of the load is 2 feet. So this is going to be 2 feet. Can't cross that off. We've put that on there. Length from the wheel axle to the axle of effort is 5 feet. So this is going to be 5 feet. All right, and I can cross that off. Boom. I've have everything in my drawing. The only thing that I am lacking is I have this arrow here, and this is going to mean by force, right? Effort, and this is going to be my force resistance. So what's the ideal mechanical advantage of the system? I'm going to have IMA is equal to DE over DR. All right, and that's what these are. D, because it's going to the effort, DE. And this one is DR because it's going to the resistance. So this is DR, distance, resistance, distance, effort. And so then now I just need to substitute those in, right? And I went and labeled those because I didn't have those. I'm like, oh, I'm going to need DE and DR to substitute. So, okay, which one's DE? Well, it's the one that goes to FE. Which one's DR? It's the one that goes to FR. So IMA is going to equal 5 feet over 2 feet. And when you solve that, right, the feet cancel. So it's not going to have any units. And that's going to be 2.5. I can do that math in my head. So problem number 6, using static equilibrium equations, calculate the effort force needed to overcome the resistance force in the system above. Okay, so this is basically saying how much force do I need to exert here to get it into static equilibrium. okay, where it's balanced. So we're going to use those same two formulas that we used before. Moment is equal to force times distance, and we're going to use moment of resistance is equal to the moment of effort. So then we just need to do just like we did before. All right, we have the moment of resistance and we have the moment of effort. And those are going to equal force times distance. So in the case here, this is the resistance, so 200 pounds times the distance of 2 feet. And then I have 5 feet for the moment around the effort, 5 feet, times the force effort that we're trying to find, right? I don't know this one. I'm pointing up here to this one. I don't know what this is. Okay? And so now I can use this equation, right, that says, okay, these have to be balanced. So in this case, what's on one side? 200 times 2. That's feet. So 200 pounds times 2 feet equals 5 feet times force of effort. All right, and I can multiply that together and do my math. 400 feet, 400 pound feet is equal to 5 feet FE divided by 5 feet. So all that cancels. Divided by 5 feet here. Okay, so so these feet canceled, so that's going to leave us with pounds. All right, and so 200 times 2 divided by 5 is going to be a effort force equal to 80 pounds. Okay, no, that's a little hard to see, but normally once you get it set up to 200 times 2 is equal to 5 times FE, you can do the math from there. Okay, so a medical technician uses a pair of 4-inch long tweezers to remove a wood splinter from a patient. The technician is applying 1 pound of squeezing force to the tweezers. If more than 15 pounds of force is applied to the splinter, it will break and become difficult to move. So think about a pair of tweezers, right? They kind of look like this, right? And you put your fingers here and here to squeeze them together, and the force is here at the end, right? And the fulcrum is going to be at the other end. Okay, so there's where you squeeze in the middle, force is at the end, fulcrum is at the other end. Okay, so we're just going to draw half of that. All right, so I'll draw fulcrum at one end, and the tweezer goes out. Right, I have a force that I am putting, so that's my force effort. And then I have the resistance force, which is the object that I'm squeezing. All right, so that's the force resistance. All right, so all right, we know that they're applying 1 pound of force, so we can say this is 1 pound. And scratch it off. If more than 1/5 of a pound of force is applied to the splinter, all right, so we can say this is 1/5 of a pound. All right, or you can do 1 divided by 5 in your calculator and say, oh, you know what? That's really 0.2. All right, pounds. I like decimals. Okay, so I've got my FE, I've got my 1 pound, I've got my distance to my effort. And notice I'm putting in the same things each time here. Here's my distance to my effort. All right, and if we go down here, all right, my distance to my resistance is 4 inches because it's 4-inch long tweezers. Okay, so now we have that drawn out. What's the actual mechanical advantage of the system? Well, AMA is equal to FR over FE. Substitute AMA is equal to FR, 0.2 pounds, divided by FE, and that is 1 pound. Anything divided by itself is itself, so AMA is equal to 0.2. Remember, pounds cancel, so there's no pounds attached to that. The next thing is using the static equilibrium equations for number 9. Calculate how far the fulcrum, how far from the fulcrum the tweezers must be held to avoid damaging the splinter. So my formulas are still the same. Mass equals F times distance. MR, I'm sorry, not mass, moment. Moment resistance equals moment effort. And we're going to do both sides again. So ME, MR. And if we pull from the other page there, ME, so force of 1 pound times, we don't know what DE is, so we're going to have that be blank. And then we have MR of 0.2 pound times 4 inches. And then now I have my two sides of my equation, so I can put them on either side there and say MR equals ME. So 0.2 pound times 4 inches equals 1 pound times DE. And then I do all my solving there. Basically, we divide by 1. We get D equals 2 times 4, or 0.2 times 4. All right, and so our DE is going to equal 0.8 inches, right? Because when I do that, pounds are going to cancel when I divide by 1 pound. Divide by 1 pound, right? Those pounds are going to cancel, leaving me only inches. So that brings us to the wheel and axle. What is the linear distance traveled in one revolution of a 36-inch diameter wheel? This is simply circumference. So circumference equals pi times d. Substitute circumference equals pi times 36 inches. That equals a circumference of 113 inches. An industrial water, An industrial water shutoff valve is designed to operate with 30 pounds of effort force. The valve will encounter 200 pounds of resistance force applied to a 1.5-inch diameter hole. Diameter axle. Sketch and annotate the wheel and axle system described above. Okay, so this one's really simple. Okay, I have a axle that has a diameter, and I'm going to draw a little arrow, a diameter of 1.5 inches. It's super helpful to just go ahead and do the radius when you do these problems, the radius. right, is going to be 0.75 inches, half a diameter. I'm going to have the wheel portion. That's going to be the diameter of the effort. I don't know what that is. And I know that the force resistance is equal to, what is it equal to? Force resistance is equal to 200 pounds. 200 pounds. Force effort, 30 pounds of force, 30 pounds. So what is the actual mechanical advantage? AMA, same formula we've been using, is equal to FR over FE. AMA, substitute, FR, 200, divided by FE, 30. That gives me an AMA, pounds, pounds, pounds cancel, AMA of 6.67. What is the required wheel diameter to overcome the resistance force? All right, so this is, all right, diameter resistance. This is diameter effort. We know, right, that mass equals force times distance, and remember, that's as long as it's perpendicular. I'm sorry, moment is force times distance as long as that's perpendicular. Moment of resistance is going to equal moment of effort. So let's go ahead and take the time and write these down. All right, so we're going to do moment of effort. That's going to be 30 pounds times the diameter that's perpendicular. Moment of resistance, 200 pounds times 0.75 inches. All right, the radius of this. So, by the way, I may have said diameter. This is distance, right? It's going to be the radius. Okay, that may confuse people because you see diameter. Normally, if I want diameter, I will make the diameter symbol that you can't see, right? The diameter symbol. Okay, this in this case is the distance perpendicular. So don't get that screwed up. That's a super common mistake. All right, so ME, MR. All right, we can put that together. So 200 pounds times 0.75 inches equals 30 pounds times the distance that's perpendicular. Okay, just so you know, the distance perpendicular is going to be the radius of the wheel. Okay, so then the distance perpendicular is going to be right. So we can substitute that in, right? So we're solving this equation. 200 times 0.75 is equal to 30 pounds times the distance that's perpendicular. Distance perpendicular is the radius. Okay, so if we go ahead and we solve this, 200 times 0.75 is going to leave us 150 pounds. All right, times inches divided by 30. So I'm divided by 30 to get on the other side. All right, and that's going to be equal to 5. And then DE, 2 times 5 is equal to 10 inches. So the final answer is the diameter of the wheel, can't type, WHEEL, right, is equal to 10 inches. All right, now, okay, you probably got lost here, right? So just think about the math. 200 lbs times 0.75 is equal to 30 pounds times the distance perpendicular, otherwise known as the radius. All right, so I'm just going to scratch that off and put the radius there. All right, 200 times 0.75. All right, that's going to be 150. Not 0.15, 150 pounds. All right, and then we have 30 over here, so I need to divide by 30. Divide by 30. Okay, and then you continue on to solve it, and that's where we got to 10. Okay. The only part, so when you go ahead and you finish this out, remember this is in radius, right? And the reason we multiplied it by 2, because we get 5, right? When we do this, this is equal to 5, right? But it's a radius, so we have to change that into a diameter, and that's multiplied by 2. So that's why it jumped to 10. I could have done a better job explaining that. Sorry. All right. This video's gone on long enough. Let's take a break, and I will break it into 2 sections, I think. Thanks.